Okay. Okay. Thank you. Okay, good afternoon. So I'll be talking about continuous software quality analysis on Atlas. So to start with, just a definition. So to do any kind of software quality analysis on a large code base, you usually use software defects as a kind of unit of measure. So I've just highlighted a few examples here. So it could be that you have redundant code paths in your code that don't get used anymore and there's no coverage. It could be errors of omission. It could be things like uninitialized variables in your code. Or it could be something like an inefficient use of allocated memory. So you may inadvertently introduce memory leaks in your code. And importantly, software defects may not be flagged by compilers. So you may argue it compiles, it runs, who cares? You know, what's the problem? It's really, when you look at it at scale, that it becomes a problem and it becomes important. So if left unchecked, the accumulation of defects can result in performance degradation. All those memory leaks add up. And also problems with the long-term sustainability of the software, especially if the code paths don't get used, the provenance is not known and so on. So, on experiments such as Atlas, the regular application of software quality tools is pretty much essential to reduce software defects down to an acceptable level. You'll never get to zero, but you need to put an upper cap on the defects that you do have. So on Atlas, we have close to 6 million lines of code. We have hundreds of developers based worldwide, and the code base has been there for several years. So these things do accumulate, and this needs to be monitored. So my role in the experiment is to, as a software quality coordinator, is to run tools like CPP check and severity, which are static code analysis tools that regularly scan the entirety of the main software release, looking for defects, as illustrated on the previous slide. These results then are made available through custom portals. For commercial tools, there's a Connect interface that people can log into and then filter on for their defects and to track them on their resolution. And we can also trigger scheduled notifications on any urgent defects to code maintainers to replace into the next release. From the developer viewpoint, there's more general code quality indicators, coverage testing tools, such as GCOV, code formatting checkers, such as Uncrustify, that are applied, that are used as part of the development and build process. And these are pretty good. The defect identification works, and uninitialized variables and sources of memory leaks are generally dealt with promptly. But other defects in non-critical sections of code often remain unresolved. When non-critical is a subjective term here, so it's one person's non-criticality is another person's criticality. So that really needs, there's no kind of one fixed way of determining which is critical and which isn't. And then you can see on the right-hand side, this table here, a kind of evolution of the defects by age. And you can see that you've got, over 12 months, you see you get this kind of backlog of defects identified that have not been resolved. And this backlog can be for a number of reasons. So there is, in some cases, the responsibility or the provenance of the code is unrecorded. So no one really knows who wrote that piece of code 8 years ago and whether it should be changed in such a way that it won't break anything else. And that developer effort is reorganized or not retained. The developer moves on elsewhere to industry or works on a different subdetector or something. So that isn't really formalized at this stage. So how do you address something like that? Well, you could periodically reevaluate and disregard any defects where the impact is marginal. So say have a cutoff of 12 months and have an amnesty, and if it doesn't look like it's going to affect everything, just forget about it. Now that's kind of it's not as satisfactory, but it's pragmatic and would work. But the second point, which is what I want to talk about today, is to identify and address defects before they are introduced into a software release, rather than looking post facto. Just look and try and capture them on the fly. Now, to do any kind of work, any initiatives in this area, you need to consider our new software build infrastructure. But because of inspired scheduling, I don't have to talk about this in any great detail because you've heard about it already. So yeah, we have the source code management is Git. We use it through GitLab. We have a merge request process now, so we can perform code reviews with a dedicated rotor of code review shifters in place to validate any changes. And then coupled with that, we have continuous integration where we have lightweight testing and build correctness checking for each modification that's proposed by any developer. And this is kind of best illustrated by this kind of a screenshot of the code review process. This is a GitLab discussion panel. And as you saw before, you have a discussion, and then once a merge request is opened, then any code modification is passed and triggers a continuous integration job on a Jenkins server. It runs these tests, and then the results are then fed back into the discussion panel, as you can see here. And then the review shifter then looks at the results, and if it passes, then they can progress the review. They can change the label, and then the review can be eventually approved. So yeah, this new framework is an ideal opportunity to apply software quality checks as part of this new process. So code review shifters can catch the defects as they are introduced. If we can identify them at this point, they can be quashed at that point. Even if they wade through, defects are audited at source for free as part of this discussion. So you can always go back 6 months hence and see, well, why did we let this defect pass? And you can review the discussion that was had. But in order to do this, there's some practicalities in play. So the CI tests, for example, would have to be quick. You saw that the typical CI chain is 3 to 5 hours, but we certainly wouldn't want to significantly add to that. So something like less than 5 minutes would be ideal. We don't want to apply any additional load, and you expect a reasonable response time for shifters to see if there's any defects in place. And importantly, because of this, you would ideally perform checks only on the code directly affected by any changes. So not the whole of the release, just what you've changed in the merge request. And then as a secondary point, the test results themselves shouldn't be acted as a blocker to any kind of approval. It's more advisory because they're not foolproof, they're not bulletproof, the defect identification. It could be a misidentification, it could be a false positive. Now, in order to add this to the build infrastructure, we didn't really want to put this on Rails essentially and develop and then confuse the developers and shifters alike. So we really needed a sort of standalone test infrastructure to test this out. In order to do this, you needed to emulate the build infrastructure. You needed to emulate the key services such as GitLab, such as Jenkins. But fortunately, it's very easy to do with containers. So container images of key services are easily instantiated. So on one site, for example, you can deploy GitLab, you can deploy Jenkins and other services as well. And then aside with that, you can have a test harness where you can have a mock test repository and mock merge requests, and then you can kind of test the response of any kind of software quality tests and the configuration of such before you then deploy to a live production system. Similarly, because you want to work in a distributed way, you want to make it portable, so you can essentially duplicate that into a second site. And that, again, very easy to do with containers. And all you need to do is have a common project area which you have a Docker registry, and then you can have some kind of rudimentary version control. So 2 people can work simultaneously on different aspects of the software quality tests. So just to take one as an example, the first one that was attempted was to provide a continuous integration CPP check test. CPP check was tested because it was very easy to run on a partial section of the software release. It's also very easy to interpret the results. It just produces XML, and then you can just read that in. Now, the actual job itself is not just a case of running CPP check. A number of things have to be considered. So at the first, when the continuous integration job runs, you have to get the merge request ID, and by extension, you can then look at the affected packages that were in that merge request. So then you have a list of explicit packages that you will run the software quality tests on. You then run CPP check or whatever static code analysis tool you want to use. This generates an XML file in this case. Now at this stage, you can just then reinterpret that and then push that back into the merge request discussion. What happens there is that even maybe innocuous changes could affect hundreds of packages, and so you'd be flooded with possibly hundreds of defects, and it wouldn't be clear to the shifter whether they need to act upon any of them. So early on, it was kind of considered that the most important information for the shifter and developer alike was more a state change. So defects, in this sense, are either introduced, or they're removed, or they actually remain unresolved against some kind of reference result, where the reference result is the quality to run across, say, a nightly build or the latest build. So in this sense, you then load the analysis and the reference results in together, both in XML format. You compare the defects between the results, and then you define a tag state, and you define these tag states to the selected results, and then publish to a review discussion. And this is the kind of sample report, and the kind of bulk of the work is gone into sort of trying to get this into a kind of human-readable form and also to prioritize and truncate so you kind of like can direct the shifters into what is important. For example, indicating if any defects were introduced by that change, forgetting about the old stuff, just saying, has anything new happened? So making sure you stop the rot, making sure that you're not introducing anything new. So in this case, not. And then you can also have, you can look at the files, any defects in the files that were changed by the merge request if they are, highlight them, and it may be the case that the developer is also the maintainer of the package, and they may want to resolve these as well, and so on. So it's yeah, and this, so you just essentially create a markdown report, and then GitLab does a very good job of formatting that. So that's CPP check. You could also look at other software quality tools. So you could also look at tools like Coverity, and that's kind of a bigger goal really because it's more comprehensive. The problem is that the full build analysis and commit steps for Coverity are very long. It's 30 hours. Speaking to Coverity, the Coverity support, you can investigate use of incremental builds and desktop analysis methods to get that down, and that's very much an investigation. But yeah, it's a similar comparison and reporting mechanism, and it's not limited to Coverity. You can apply any kind of static code analysis tool and report back to the workflow in the same way. Also to be considered is the software code quality indicators. So in this case, you're looking at kind of more holistic metrics. So for example, the number of lines of code with comments, for example, right down to sort of more enhanced things like cyclomatic complexity, i.e. the number of paths that you can go through a piece of code. And there's a number of paths in a code section. But it's not clear how you would best interpret this, so you could just do this in the same way as we did before with CPP check. But single value quality metrics are not that instructive. So you could say, well, there's 234 lines of code with a comment attached. Is that good or bad? Well, who knows? So instead, you've got to capture trend information and then put that into context. So if it was 234, has it gone up by 65%, or has it remained the same? And then you have some indication of whether any action needs to be taken. So to test this, very similar kind of workflow, but in this case, so you have like a reference builder and you have the merge request. But in this case, we do slightly different. We use Lizard as a kind of example quality indicator tool, and then convert this into a JSON format, which means that you can then post this into Elasticsearch. You can create an index in Elasticsearch, and then when you look at the merge request and you look at any changes, you can just poll in Elasticsearch and determine if there's any significant changes have been made and publish the results as before. By doing Elasticsearch, you can also then provide dashboards, and you can do threshold monitoring and so on. So it is as a kind of proto example. I looked at 15 snapshots of a full release, but bearing in mind each release has over 51,000 files, 219,000 functions. It's the order 50 megabytes of data ingested on each run, so it does add up. And so yeah, you can see there that injected some fake code to increase the cyclomatic complexity. It does pick that up. Okay, and just the final piece of the jigsaw here is the triage options. So really, it's better to promote reviewer-led triage, i.e., if there's any kind of unimportant or incorrectly identified defects, the reviewer can sort of flag that as such and essentially blacklist them so they don't appear in again, rather than just rely on a single person. So you could do this very simply by maintaining defect suppression lists. So just have a global list, and then make sure that your CI job references that and doesn't report it if it sees it on the blacklist. But you still kind of means that it has to be maintained by a single person. So what you could do is you could use a Coverity-based triage data. It backs it with a database that stores triage information, and you can just open this up. You could use, for example, you could use GitLab webhooks, so you can have some kind of sample sort of pseudo command written in the discussion panel. The webhook would pick this up, throw it to a listener daemon, and then there's an API connection to Coverity Connect, and this would then manipulate these fields, and you would store this on the database without any additional features in place. So yeah, so there's many other things you can do on top of that. So just to wrap up, I mean, yeah, how far do you go without actually just trying another tool? So for example, SonarQube is one possible solution, and it provides an alternative option and looks pretty good. But as kind of touched upon earlier, I mean, the emphasis really on Atlas is to consolidate all these kind of the myriad of tools and services, and then kind of make it work for our chosen workflow now, rather than just another thing. So if it looks like SonarQube would fit into that, that's fine. But at the moment, we could just try something a bit more lightweight and more harmonized. Attribution, so the responsibility aspect has been touched upon. And then also developer-led defect analysis. So really kind of encouraging, this is more sociological, but developing, ensuring that the developer checks software quality before they commit their code. And you can do this through pre-commit hooks in Git. There's also IDE plugins through Coverity and so on, so that you're not relying on the review shifter to pick these things up and triage them. Okay, so just to finish off, so continuous software quality evaluation for Atlas can be achieved by lightweight defect testing and continuous integration and part of the code review process. And the accumulation of some experience as we're kind of going through this kind of testing phase will help tune defect testing and the results presentation so we get the most out of it. We've kind of looked into an insight of more enhanced code quality reporting, as you can see with using tools like Lizard, and there's much more besides, and they could prove useful as well. And then sort of lastly, but not least, is that these chosen solutions are project agnostic. We're not Atlasified anything here. So it's greatly helped, and this has been greatly helped, as touched on before, that by the recent migration to kind of wider community tools like Git and GitLab, rather than relying on bespoke or legacy tools. So in that sense, if there's interest, similar approaches could also be applied elsewhere without loss of generality. Okay, thank you.
Can you say something on the false positive rate of the static checkers?
Yeah, I would pick numbers out of the air. I mean, it's kind of over 10, 20%, but it depends on the code. It's hard to say because some of it is just subjective. So I mean, I think we have a blacklist of about 500 or so bits of defects, and we have about 3,000 defects in play. So yeah, but it's kind of more subjective. It's more for the person to decide whether it's a false positive rather than kind of clearly identified as such. Yes, in fact, well, I mean, they overlap a little bit. As I alluded to, Coverity is kind of more, you have a huge array of checkers, whereas CPP check is more lightweight, but there is an overlap there. But certainly Coverity does pick up a lot of false positives that we have to kind of ignore by hand, and this is kind of what we want to avoid because it's very difficult to track for a shifter to understand what is unimportant and what's a false positive. So we need to be a bit more programmatic on that front.
So I'm a huge fan of these tools that help us improve the more generic, not more generic, but qualities about code like code smell and other things like this. So I fundamentally believe these are valuable. But I was wondering, are there any figures of merit that we have in Atlas which show that this work is improving, either reducing the number of bugs, making the code easier to maintain, or has anybody done or tried to quantify if this work is helping?
Yeah, it's difficult. I mean, because the simple metric is just number of defects resolved, for example. But then, like, is that important in general? I mean, because I think what you found really with the prioritization is the low-hanging fruit is like, oh, initialize variable, that's easy to do. But some of the kind of more sort of general code quality, like number of comments or kind of like, path through the code and so on. It's like, for some people it's like, who cares? But for other people it's like, well, it's important for the readability. So it's, to actually take a step back and try and analyze that is difficult.
I guess I'm thinking of, because those are all self-generated metrics, right? You've decided this is bad, and therefore if this improves, you've actually made progress.
Yeah.
I mean, for example, per release, the number of crashes that happen on the grid, is that falling? Or, things of that nature.
Yeah.
They're important to our physics somehow.
Yeah, and that's a good point. As to far my knowledge, I mean, there isn't any sort of rigorous studies. But then, I mean, this kind of, once this is baked in, these kind of meta studies essentially can be done, and we can kind of we can evaluate whether any kind of sort of the defects has gone down. Has it actually improved the quality of the code? As the number of crashes decreased? And we can actually do those most studies. But at the moment, it's kind of just identifying the defects and trying to reduce that. And so, yeah, we're kind of a little bit blind in that respect.
Yeah, I was wondering why, I mean, when I was in Atlas, Coverity was already being used, but it was always a bit a pain in the neck already at that time because it was always lagging a little bit with regard with the C++ standard that we were using. And I know that CMS was using coverity and then migrated to Clang analysis for this same reason. I was wondering whether the track record of coverity in that regard.
So we just recently moved to the latest version of Coverity, which has got like C++ 14 support and the like. But yeah, I don't know about Clang actually. Yeah, I mean, yeah, we don't want to kind of bet the farm on Coverity. I mean, that should be one of several tools that we have, but it's a good one to use. But you're right, it doesn't necessarily cover everything. But from what we moved from major jump from 7.7 to 8.7.1, and it seems to sort of picked up a lot more that didn't previously. So maybe that's good enough. I don't know.